And let's work on this. And I am on page 8. Good. So first of all, I have to find the function, the family of functions if you want. So this is 3x to the third over 3 minus 5 x squared over 2 plus x plus a constant c. Let's check. Bring down 3, simplify, and I get 3x squared. Bring down 2, simplify, and I get negative 5x. Differentiate x, I get 1. Differentiate c, get 0. And now I'm given f of 1 equals 7/2, which, oh, let me simplify. That's fine. So f of 1 equals 7/2 means 1 minus 5/2 plus 1 plus c equals 7/2. So this is 2. 2 minus 5/2 plus c equals 7/2. I don't want to add because when I move everything to the other side, the fraction, I realize it will go away. 7 over 2 plus 5 over 2 is 12 over 2, which is 6 when I move it, and minus 2 is 4. So 7/2 plus 5/2 is 12/2, which is 6. But then minus 2 is 4. So the function, the unique function that fulfills the given conditions is this. Guaranteed that it passes through this point, and guaranteed that it has this derivative. Any questions on this? Okay, let's take a look at a word problem. What about demand from marginal demand? What about heart rate?
Can we do number 69?
Okay, heart rate. Very good. Let's do heart rate. Let's read it. So the rate of change in Tricia's pulse in beats per minute, T minutes after she stops exercising is given by. So this is 69. And we have, and this is the page 380. So r prime of t equals negative 46.964 e to negative 0.796 t. Perfect. Find r of t if Tricia's pulse is 78 beats per minute, 2 minutes after she stopped exercising. Okay? So what is this? What does this mean? They're asking us to find that particular function. This is the derivative, and this is the function. Knowing that when when t is 2, r of t is 78. So the point is 2, 78. Good. So let me stop sharing. Good. So let's find, first of all, in part A, let's find r of t. So the number in front will never bother us. I integrate this, and we know the rule, so it's e to negative 0.796t divided by this number, and plus a constant c. Yes, I will divide these two to see what's in there. So I'm going to share my screen. You don't need this. You can just give me the number. If not, I will do it. So it's 46.964 divided by 0.796. Okay, let's see what we get. Did I enter it correctly? I think I did. And oh, look at that. Brilliant. That was nice. 59 e to negative 0.796t plus a constant c. They are giving us this point. When t is 20, it's 2 minutes, r of t, it's 78. So this will enable us to determine c. So r of t is 78. Then we have 59. E to negative 0.796 times 2 plus a constant c. So c is 78 minus all this. So let's write it. So c equals 78 minus 59 e to negative 0.796 times 2. Careful how you enter in the graphing calculator. Let's do that. So I have 78 minus 59. It was 59, right? Yeah. 59 times e. E is right here with natural log. You know me, I have to have parentheses everywhere. So negative 0.796 times 2 and close. So this will be our C. 65.99. So C equals 65.99. So then R of t is a unique function for this lady. 59 e to negative 0.796 t plus 65.99. Let me share my screen again and continue. Not here, but here. Find Trisha's pulse rate 4 minutes after she stops exercising. Okay, that's not a big deal. I didn't mean to do that. I meant to do this. So I will punch in the function. And what is it? 59 e parentheses negative 0.796 x and close and outside plus 65.99. And second and graph, and I want 4, they said. So 68.43. So R of 4 is 68.43. And this is, oh, I didn't mean to do that. So, and this is in beats per minute. Okay? Because this is the rate of change. That's why it's in beats per minute per minute. But R of t, the function itself, is in simply beats per minute. Okay, I put it in. Find the rate of change in Trisha's pulse after 4 minutes. Okay. So now I have to use, because it says the rate of change, so this was part B. So in part C, they want us to plug in here to see the rate of change, to plug in 4. So R prime of 4 will be negative 46.964 and times e to negative 0.796 and times 4. So let's see. I'm going to share my screen. Negative negative 46.964 and times e to negative 0.796 times 4. So it was changing at negative 1.95 beats per minute per minute. Okay. How can R of t and R prime of t be used to find Trisha's resting pulse rate? Resting pulse rate. So when time is 0. Okay, so actually resting when time? Very good question.
That be
So yes. So at 0, so when time is 0, I have to find R and then plug in and determine C. But go ahead, Nick. What did you have in mind?
Well, when T is 0, that's when Trisha, like, she's just stopped exercising. So that wouldn't be resting pulse rate, though. Wouldn't it be like the limit as T approaches infinity?
So assuming that's a very good point. Assuming that she does not continue exercising. I agree. So the limit, so assuming that, good point, but assuming that she does not continue exercising later on in an hour from now. Okay, so they're not asking us to determine it, but we have to make some assumptions here. So assuming that for the next, I don't know how many hours, right? An hour, maybe half an hour, she's not going to exercise. So we're going to plug this in like 30 minutes from now. And 30 minutes from now in the pulse function, because we need to determine a point. So like we had before, right? Let me stop sharing for a second. See, here we had a point. We had this point, 2,78. So we have to determine her pulse after, I don't know, maybe half an hour, 20 minutes, I don't know, maybe an hour. So 60 comma something. And I can plug it in because we already have the function. Here's the function. So in R of t, I plug in X number of minutes, assuming she will not exercise in between. I get a point like this, 60 comma something, and then I will evaluate, because the point is needed for the constant.
Wouldn't the constant, so I just plugged it in, the constant is the resting heart rate. So any number you plug in over 30 or
because
like
yes,
that.
so here's why. Because as t approaches infinity, as Nick said, this will approach 0. That's why this term is 0. And that is the resting heart rate. Very good point. Yes. But that's the reason why, as t approaches infinity. So as t approaches infinity, this quantity approaches 0, and 0 times 59 is 0, and that's how we get the 65.99. Initially, I was thinking that they're asking before she started exercising. How can R of t and R prime of t be used to find Trisha's resting pulse rate? Which is the same thing. Okay? How come it's the same thing? Because before she starts exercising, t is 0. That was my thought, which is the same thing. So if you say t approaches 0, or t equals 0, or t approaches infinity, you will get the same answer. So before she exercises, time is 0. This term, oh, actually, this term is 1 with time at 0. But so e to 0 is 1. So we don't know what she did before. So that's a question here. Why wouldn't before I start exercising, why wouldn't my resting heart rate be this? So the moment I start exercising, I guess I'm getting excited.
Well, but 0 isn't like before you start, because it's
But that's what
the function is saying when she stops exercise, when she has completed her exercise, it's T minutes after she stops exercising.
She stops exercise. So the function does not start before she starts exercising. The function starts after. Okay. Good point. Yes, after she stops exercising. So in that case, we cannot use t equals 0. Only t approaches infinity. But again, there is another assumption here. I don't know whether maybe in an hour or 2 hours later, she's a, I don't know, a Zumba instructor and she's going back in. So I'm not sure about this infinity. So the problem has a little bit of a problem, I would say, with that assumption. But assuming she's not going back exercising in the next hour, then, you know, if you put in 60, we can look at the function and put in different values and see how fast this piece goes to 0. Probably it does. I'm just curious now, since we're discussing that, just for a second. See, I have the function in there, 59, it's our function. So I just want to see a few values of x. Okay, so let's say 20 minutes. So to see how fast is approaching 65.99, that's the question. So 20 minutes. Okay, so in 20 minutes, it's already there. Okay, so that piece goes to 0 very fast, the first part of the function. Okay, 10 minutes later. Okay, 10 minutes is not good, but probably from 15 on, yeah, okay, 10, 15. Okay, so this is normal, I'm assuming, for the heart rate to go back down to normal in about 10 to 15 minutes. Okay, that's what I wanted to convince myself of that. So that's a good point, but of course not infinity, because we don't know what's happening. Good, excellent pick. Good discussion. Thank you. Okay, do we want to, no, not that one, this one. Do we want to look at anything else?